So question 3 represents some things our textbook called maybe advanced solving techniques, looking inside and fraction busters. They had looking inside, undoing, and I can't remember the third one, but fraction busters was also an advanced technique that they talked about. Anyways, this first one, if I look at it, it's the square root of something. In fact, I don't really care what this thing I'm highlighting in yellow is. All I know is that the square root of something is going to equal 6. Well, because I know a bit about arithmetic, I know it's the square root of 36, right? 6 times 6 is the 36. So I know that this thing inside, the 3x plus 9, must be 36. And if it is 36, then when I take its square root, I most definitely will get an answer of 6. So I'm just saying, let's let the thing inside be 36. Now, if I take away, let's see, take away 9 from both sides, 36 minus 9. I'm just thinking that 36 minus 6 is 30. Take away another 3 is 27. So I end up with 3x is 27. And if I divide both sides of that by 3, I end up getting that x must be the number 9, right? 27 divided by 3 is 9. So I've got that x has to be 9, and I can verify that quickly, right? If I look at 3 times 9, that's 27, and 27, 27 plus 9, 27, 28, 29, 30, yeah, it becomes 36, and the square root of 36 is 6. So this is most definitely the answer, right? X is the number 9. Okay, so let's look at the next one. This was a little difficult. We definitely looked at several problems like this. This was not exactly like the problem on the study team test, but it's definitely similar to it. So here's the big insight for this problem. And right now I got to be honest, the only way that I can ask you questions like this where you see the variable in the exponent is if this is possible. So when you see the variable in the exponent, ask yourself, is there a way that you can rewrite it or manipulate it so the bases are the same? And here's my insight. This number 9 is the same thing as 3 squared. So if you look what I'm doing, I'm taking the number 9 and I'm rewriting it as 3 squared. Now on the other side, I have 3 to the x minus 1, right? Now, I am going to take this power to a power rule, right? Power to a power rule. So if I want to raise a power to a power, I need to multiply this 2 times the x minus 7. So I need to multiply that out. So, and again, that's chapter 2. You can look at Laws of Exponents. So I can rewrite this as 3 to the x minus 1, and that equals 3. And notice how I distribute this. 3 to the 2x minus 2 times 7 is 14. Okay? X minus 1 is the exponent on my left-hand side, and 2x minus 14 is the exponent on the right-hand side. Let's get back up here. Where'd that problem go? Now, the thing that I'm seeing here is that these both have bases of 3. And the only way these can ever be truly equal to each other is if their exponents are the same. So this is a form of looking inside. I'm looking inside the exponents, and I'm saying, look, the exponent on the left-hand side has to be identical to the exponent on the right-hand side if these are going to be truly equal. So I can say, hey, x minus 1 has to be the same as 2x minus 14, right? So this is a pretty straightforward equation to solve. So I'm going to take away an x from each side. I get negative 1 equals x minus 14. And then I'm going to go ahead and add 14 to both sides. Plus 14, plus 14. And over on the right-hand side, we have just the x left over. On the left-hand side, we have positive 13. So x must be the number 13. So you can actually verify this, right? If you put an x into each the left and right hand side, right? 9 to the 12th power, and if you look at that, I think it's like a 5-digit number. 9 to the 12th, or 3 to the 12th power is the same thing as 9 to the 13 minus 7. So that's, I think, 9 to the 6th power. So take a look at them. They're the same, but this is definitely, x is 13 is definitely the value that makes both the left and the right hand side the same. All right, and finally we'll look at an example of this technique our textbook called fraction busters. So as I look at this equation, I can see I have denominators with an x and a 3. And I can take this a little bit at a time, and that's totally cool. I can, for example, multiply both sides of this by 3 over 1, by 3 over 1, 3 over 1. And when I do that, over on the right-hand side, notice what I get. I get 5 times 3 over 3. I just made a giant 1. Look, by multiplying both sides by 3, I made it so that this is no longer a fraction. It becomes 15 over 3, which is just plain old 5. I just busted up that fraction. On the other side, I still need to multiply both of these terms by the number 3 over 1. And when I do that, 3 times 6 is 18. So I have 18 over x, and then plus the number 3. So I definitely destroyed one of the two fractions I have, right? 5/3 is no longer a fraction. It's just the number 5. Now I can do the same thing again. I'll use green this time. This time, instead of, I'm gonna bust up this fraction, right? And if I want to bust up this fraction, I'm gonna multiply both sides by x over 1. X over 1. Now, when I do that, in the first case, like, look at this. I'm gonna get, come back. Where'd you go? There you go. I'm going to get, in the first case, if you look at it, it's going to be 18, or x times 18 over x, right? In other words, this will form a giant 1. So this fraction will be busted up, and I'm just going to have the number 18. Look at it. 18x over x is just plain old 18. I have to multiply the 3 by x over 1, which is going to make it 3x. And I have to multiply the 5 times x over 1, which is going to make it a 5x. The next thing I'll do to both sides here is subtract 3x. And oh, I'm so happy I don't have any fractions to deal with. They're gone because they've been busted. On the left-hand side, I have 18, and on the right-hand side, I have 2x. And then I'll just divide both sides by 2. And I get that I get a 9 on the left-hand side and an x on the right-hand side, so x must be 9. And again, very worth it to grab your calculator and verify 6 over 9 plus 1, and then verify that that's 5 over 3. And it most definitely is. X is 9.